Hello, I am Ahmed Abdo from the Technical University of Munich. I will present gaze enhanced cross modal embeddings for emotion recognition. This is joint work with Ekta Sood, Philip Muller, and Andreas Pulling. Emotion expressions are multimodal by its nature. Emotion can be expressed through several modalities such as facial expression, audio, gaze, body movement, body temperature, and other modalities. However, emotion recognition is often limited to one of these modalities. As in a phone call, you have access to only the audio signals to the person you are talking to, but you are still able to do the recognition task. Emotion recognition in the context of machine learning is predicting the expressed emotion by training a machine learning model using certain features. One way is monomodal learning, where a source of an input or a modality is given to the model during training time and the same modalities is used at testing time. For example, a model that uses audio signals during both training and testing to perform audio-based emotion recognition. Emotion recognition can also be done through multimodal learning, which is by training the model by more than one modality and using the same modalities at testing time. For example, a model that uses facial expressions, audio signals, and gaze signals at training time would also require that all of these modalities to appear at testing time. Multimodal learning often shows better performance at the tasks which are multimodal by its nature, such as emotion recognition. More recently, cross-modal learning has been introduced for the emotion recognition task. In cross-modal learning framework, a model that can learn a task from different input modalities that would only require only one of these modalities at this time. In the phone call example, a cross-modal learning framework would be a model that uses multiple modalities during training time to enhance its performance at audio-based emotion recognition. Gaze in emotion recognition. Eye gaze behavior has been studied widely in psychology of emotion expressions and perception, and has been shown that gaze can reveal information about the user's attention and intentions. Also, specific eye movements behaviors as gaze direction coupled with facial movements are relevant when expressing and perceiving specific kind of emotion classes. The use of perceived gaze direction has been shown to better assist humans to distinguish between emotion classes. Despite all of the works in the emotion recognition, to the best of our knowledge, no emotion recognition approach incorporating gaze with both facial expressions and speech has been proposed. From these points, we introduce our contributions in this work as follows. First, incorporating an explicit representation of gaze in the said cross-modal emotion recognition framework. Second, this proposed framework improved over the previous state of the art for video-only and audio-only emotion recognition. Finally, ablation experiments for which gaze features set to use and how specifically to integrate these gaze features in our cross-learning framework. Here is our cross-modal embedding framework summarized in this figure. We start by extracting audio features and passing them through audio encoder to get the audio embeddings. Simultaneously, we extract the facial and gaze features and pass them to the gaze enhanced visual encoder to get the gaze enhanced visual embeddings. These two embeddings, audio and gaze enhanced, are living in the same space and we call that the embedding space. For how we get the gaze-enhanced visual embeddings, we propose a novel gaze-enhanced visual stream network. This network incorporates a dedicated gaze representation into the visual stream, mapping both visual and gaze features to the same embedding space. And the integration of these two input modalities can be done in two ways. First, after processing each feature stream with its corresponding encoder, we concatenate both embeddings to form a double-sized one. Then, projecting them to the embedding space with a projection layer, and we call that model level fusion strategy. Second approach, we concatenate the raw features before being passed to a single encoder that process and projects them to the embedding space, and we call that an early fusion strategy. The next part is the triplet training, which allows the embeddings that belong to the same emotion class to be similar to each other in the embedding space, regardless of their input source, and allows the embeddings to be dissimilar if they belong to different classes. While the triplet loss imposes these said constraints on the embedding space, these embeddings are used to train the shared classifier in joint fashion. This classifier takes an embedding from the embedding space and maps it to one of the emotion classes. This classifier is agnostic to the modality of the embedding, which allows the classifier to use both the audio and visual embeddings alternatively while training. These said points, audio and gaze enhanced visual stream, triplet training, and joint training summarizes our cross-modal learning framework. And for the features used in this framework, for visual features, we first applied the open face tool over each video to do the face detection and alignment per frame, and giving these detected faces to the VGG face network and extracting the features of the VFC7 layer. OpenFace is an open source toolkit that do facial landmark detection, facial action unit recognition, and eye gaze estimation. For the audio feature, we used OpenSmile toolkit to extract the EG Maps feature set for each video, while for the gaze feature, we used the OpenFace output, especially the gaze estimation, as base features. Then we calculate statistical features upon these features as maximum, minimum, average, and others. We used the calculated statistical gaze features in two ways. First, we extract the features of window of 1 second, resulting in as many feature values per window as there are frames per second in the input video. This window-based feature can be used both in the early as well as the model level fusion, as they can be aligned with the frame-wise facial features. Second, in the model level fusion scenario, we also investigated a version of the gaze feature where we average the features that we were first computed on the window level across the whole video. In this work, we used the 1 minute gradual emotion or the OMG behavior dataset. The dataset consists of 567 monologue videos collected from YouTube with an average video length of 1 minute. The dataset is suitable for the emotion classification task, as each video is labeled with one of the 7 categorical labels: neutral, happy, sad, anger, disgust, fear, and surprise. And it is clear that the annotation were focused on neutral expressions, with fear and surprise being less common, and this is common behavior for the emotion expressions collected from in the wild videos, which is the case of the OMG behavior dataset. This is a random sample of 1 frame for each gaze direction: left, right, up, down, and straight from the set of the frames where face detection and gaze estimation was done with high confidence by OpenFace. For the results, this table shows the F1 scores for different experiments. The best video-only method was averaging and model level fusion, while the best audio-only is windowing with early fusion. Both these experiments improves over the previous state of the art for video-only and audio-only, and also over the no-gaze experiments. To gain deeper insight into the performance of our gaze integration method, we conducted a performance analysis per emotion class. We are first to give this class level performance for the OMG dataset. We compare the performances of our gaze-enhanced cross-model triplet training approaches to the corresponding no-gaze applications. For video testing, we observe an improvement for our gaze-enhanced method for the classes neutral, happy, and sad. On the other hand, our gaze-enhanced method obtains lower F1 scores for anger and disgust. The improvements are aligned with the number of the training samples available for each class. Our gaze-enhanced approach improves for the classes with high number of training samples, but has a disadvantage on classes with low numbers of training samples. For audio testing, our gaze-enhanced approach improves for the classes neutral, sad, as well as anger, and is on par with the no-gaze baseline for happy. Our gaze-enhanced visual stream utilizes a set of gaze features proposed for emotion recognition by Oddwire. A different set of features were proposed by Van, which is the best of our knowledge was the only other feature set proposed in the emotion recognition literature that utilizes gaze estimates extracted from standard RGB videos with OpenFace. In both audio and video testing scenarios, the best performance is achieved using the feature set based on Oddwire. While for the video-only testing, the features of Oddwire are always superior to those of Van, the results for audio-only testing are rather mixed. We visualized the distribution of gaze estimates for each emotion class by projecting them on the camera plane, and we plotted the kernel density estimation of these projections. The most noticeable is that the gaze distribution for sadness is very concentrated, which is in line with the passivity that is associated with this emotion. Surprise, on the other hand, is more spread out. And for the limitation for this study, a key prerequisite for every gaze integration method are the available gaze estimates. And we used the gaze estimates provided by OpenFace, which potentially missed subtle gaze cues that are not well represented in these gaze estimates. Here is a random sample from the OMG behavior dataset, which OpenFace couldn't perform the face detection and gaze estimation with high accuracy. Therefore, more accurate gaze estimates obtained from dedicated eye tracking systems should be examined in future work. We also use the OMG behavior dataset, which consists of monologue videos collected from YouTube. While this covers a wide variety of different participants and personalities, it poses constraints on the recording situation. In other words, it is only a single person in front of the camera. Future work should also investigate how our approach can be extended to handle less constrained scenarios. One example is that the recognition of emotion embedded in interactions of freely moving people. However, this poses several additional challenges. For example, gaze estimation might not always be available due to occlusions. And for the applications, our method can be applied in any HCI scenario where an RGB video of adequate quality to perform gaze estimation is available. For applications where audio only emotion recognition would be relevant is when unstable network connections results in low quality or dropped videos. On the other hand, for video only, in an educational setting, emotion recognition can be valuable to access students' evaluation or learning material, as students are often silent during learning or may be in a location with high ambient noise. Conclusion: we introduced the gaze integration into a cross-modal training framework that allows single modality emotion recognition at this time. We also introduced the enhanced visual stream network, and we outperformed the state of the art for video only and audio only emotion recognition. And the visual stream network leads to clear improvements over baselines without gaze integration. Thank you.